Hello everyone, IBM is coming with the last episode of Work, Energy and Power. You're welcome to this episode. Remember, this is solve the past paper questions. Do not forget to share the videos with the friends. This is AS Physics 9702, that is Cambridge curriculum, and we are dealing with work, energy and power. Specifically, this is part 3, and I guess it will be the last part. So remember, within these videos, you must have seen that actually we are dealing with questions relating to work done, power. You have seen kinetic energy, potential energy. Many times you are seeing elastic potential energy, efficiency, and a lot more. And I hope it is my pleasure that it is a pleasure that I take you to part 3 of work, energy, and power. Don't forget, next will be force, density, and pressure. Force, density, and pressure will be next. I believe that in part 2, we must have stopped on this page 231. And I want part 3 to start from that very point. So part 3, I'll state what's meant by work done. So this repetition of questions is just to make sure that a student gets a lot of confidence. Many times you just see the question and write without even waiting for what I'm going to say, because you have gained a lot of experience with such a question. Also, the frequency of such questions also give you an impression of how many times such questions can be asked. Okay, so work done, that is a product of force times displacement in the direction of the force. Force times displacement in the direction of the force. A trolley of mass 400 grams is moving at 2.5 meters per second. 400 grams, that is, I think that is 0.4 kilograms. Show that the kinetic energy of the trolley is 1.3 joules. So we know that kinetic energy is equal to a half mv squared. So this is going to be a half times the mass, which is 0.4 kilograms, times the speed, which is 2.5, but that is squared. So we check this on our calculator. A half is 0.5 times 0.4 times 2.5, and that is squared, which gives us 1.25. So this is 1.25, and that is approximately 1.3 joules. The trolley moves at point P as shown in the figure. At point P, the speed is 2.5 of the trolley is 2.5. A variable force F acts to the left on the trolley as it moves between points P and Q. Then the variation of force with displacement is shown there. So force is they're showing that force is directly proportional to the displacement x, because it's a straight line through the origin. Okay. The trolley comes to rest at point Q. Calculate the distance PQ. It comes to rest at point Q. So the distance, we want to find the distance PQ. First of all, let's find the work done by this force, because it's the only force acting. So it means the work done is going to be the area under that graph. So the area under the graph, or the average force times the distance, is going to be the work done. The area is equal to the area under the graph is the work done by the force, which is equal to the average force half F times X. But the work done, of course, the object had kinetic energy. If it comes to rest, its kinetic energy is going to be lost. So its kinetic energy, or the work done, is going to be a half times the average force. The force is 14. Is it 14? So this is, that is 10, 11, 12, 13, 14. So the force is 14. So this is times 14 times the distance x, because they didn't give us any value on the x-axis. So this is distance x. But that one, remember, the work done is the loss in the kinetic energy which this object had. So this is going to be equal to 1.25, which was the kinetic energy that the object had. So we just cross multiply and find the answer. So 1.25 times 2 divided by 14. So we see that the work done is 0.179. I mean, x is equal to 0.179, or approximately 0.18 in meters. On the figure, sketch the variation with x of the velocity v for the trolley moving between P and Q. Remember, at P it had a speed of 2.5, so the graph starts at T equals at P, the graph starts at 2.5 meters per second. But it comes to rest. That means at Q the speed is going to be 0. But then the force is constant, remember. Actually, the force is increasing. As we move towards Q, the force is increasing. If the force is increasing, it means the deceleration is increasing. That means the speed decreases rapidly. The deceleration is increasing. Remember, this is a graph of velocity against time, where the gradient is the deceleration. Therefore, this graph is going to be it's going to become steeper, because as the force increases, the velocity decreases, the deceleration increases. Therefore, how do we show an increase in deceleration? This graph is going to be steeper as it tends towards Q. So I will draw it like this. The line is steeper as we tend towards, it is becoming steeper as we tend towards Q. So that will be our graph. The gradient of this line is increasing as you leave P, and it is increasing as you tend towards Q. So the graph will be like that, because the force is increasing, the deceleration is increasing. And how do we show an increasing deceleration? That is a graph of increasing gradient. Okay. Distinguish between gravitational potential energy and elastic potential energy. I think this is not the first time such a question is appearing, so we shall distinguish straight away. So for gravitational potential energy, this one is energy of a mass. Energy of a mass due to its position, in a field, in a gravitational field. Energy of a mass due to its position in a gravitational field, that is gravitational potential energy. Then elastic potential energy, I will just use EPE. Elastic potential energy, we know that that is the energy stored in an object due to its deformation or being compressed, stretched, or changing shape. Energy is energy stored in an object due to its deformation that is the object is being deformed or being compressed, due to it being compressed, or being stretched, or change of shape or change in shape. So that is what we call the elastic potential energy. If there's a change in shape of an object and there's a possibility of the object to regain its shape, then it has undergone what we call elastic deformation. Okay, and therefore the energy stored is elastic potential energy. A ball of mass 65 grams is thrown vertically upwards from ground level with a speed of 16 meters per second. Air resistance is negligible. That is a very important statement. Calculate for the ball the initial kinetic energy. So kinetic energy is equal to a half mv squared. This is going to be a half times the mass. 65 grams I think is 0.065 kilograms, times the speed, which is 16 meters per second, so that is 16 squared. And this is going to be a half is 0.5 times 0.065 times 16 squared. So that gives us 8.32 joules, or approximately 8.3 joules. Then the maximum height reached. Maximum height reached. We know that at maximum height, velocity is 0, so we can use v squared equals to u squared plus 2as. Because it was thrown vertically, the acceleration is going to be negative. So at maximum height, v is 0. So I'll say that 0 squared equals to, this was 16 squared minus 2 times 9.81, then times the height h. So the height h is going to be equal to 16 squared divided by 2 times 9.81. So we just press our calculator. 16 squared divided by 2 times 9.81. So that is 13.05, or approximately 13 meters. Then the ball takes time t to reach maximum height. The ball takes time t to reach maximum height. For time t a half, time t equals, time t over 2 after the ball has been thrown. Calculate the ratio potential energy of the ball over kinetic energy of the ball. Let's first of all find the kinetic energy at a half t. We know that at a half t, the speed must have reduced to half its original value. At half t, the speed is half its original value. So let's say initial kinetic energy was equal to a half mv squared. That was the initial kinetic energy. Then, and remember this v was 16. But at t over 2, the speed v is going to be 8, because at initial the speed at t equals to 0, the speed was 16. So if the time to reach a half is t over 2, the time we are considering the motion is t over 2, it means the speed must have reduced by a half, because at maximum height the speed becomes 0. So this will be 80 meters per second. So kinetic energy here is going to be a half times the mass times 8, and this is squared, which is going to be, actually this is the same as, without even wasting time, this is going to be the same as, let me use ratios without putting any calculation. I'll use ratios. So if the speed is half the initial speed, it means I'll just put here a half of the initial speed, and this is squared, which is going to be equal to a quarter, okay, a half m into a quarter of v squared, which is going to be a quarter into a half m v squared. Remember, this was the initial kinetic energy. So if the kinetic energy at T over 4 is a quarter of the initial, it means the potential energy must be 3 over 4 because total energy must be equal to give us a ratio of 1. So it means the potential energy at that time is going to be 1 minus 1 over 4 of the initial, which is going to be 3 over 4 of a half m v squared. Therefore, it means the ratio we are looking for is going to be equal to potential energy of the ball, which is going to be 3 over 4 of a half mv squared divided by kinetic energy of the ball, which is going to be 1 over 4 over half mv squared. So that means this is going to give us a ratio of 3. That is the ratio of 3. If using ratios is very hard, we can now substitute. So remember, v equals to u plus at, and at maximum height v is 0. Let's find the time to reach maximum height. So v equals to 0 at maximum height. Initial velocity is 16 minus 9.81 times t, which means that the total time is going to be 16 divided by 9.81, the time to reach the maximum height. Then t over 2 is therefore going to be 16 over 9.81 divided by 2, which is 8 over 9.81. That is t. So we can now find v at this time. V at t over 2 is going to be equal to, I'm using the same expression, u is 16 because it's moving upwards, minus 9.81 times t. T is 8 over 9.81, so 9.81, which this gives you 9.81 cancels, 16 minus 8, that is 8 meters per second. So the velocity at half time is 8 meters per second. That is the velocity. Let's find S, because we need to find the potential energy using S. So potential energy, so V squared is equal to U squared plus 2AS. We have the height, or we want the height at that time where the velocity is 8 meters per second. So when V is 80 meters per second, initial velocity was 16 squared minus, this will be 2g times the height h. The height after t over 2. So this height h we are making h the subject. So h is going to be equal to, I'll just press my calculator. This will be 8 squared minus 16 squared. Then we divide by negative 2g. Remember, this is the same as 16 squared minus 2 times 9.81h. So I'm dividing by negative 2 times 9.81. Which gives us 9.79 or 9.786. 9.786 meters. That is the height at t equals to t over 2, at time equals to t over 2. So you can now find the ratio of the potential energy, which is mgh, over the kinetic energy, which is half mv squared. So the ratio will be, for potential energy, it will be mg times h. Then for kinetic energy, it is a half mv squared. So m has cancelled. I'm substituting the quantities. G is 9.81. So this is 9.81 times h, which is 9.786, divided by a half is 0.5 times v squared. V at that time is 8, but is squared. So we can check with our calculator. Open brackets, 9.81 times 9.8 786 divide by, open another bracket, 0.5 times 8 squared. So you see it is still approximately 3. So this is still approximately 3 or 3.0. So that is the ratio. So the answer here is 3.0 or 3. State and explain the effect of air resistance on the time taken for the ball to reach the maximum height. Of course, if there is air resistance, the time is going to be, I think the time is going to be smaller if there is air resistance, because the resultant force downwards is going to be greater. It means the average acceleration is greater, which makes the time to be less. So think of a ball moving upwards. This arrow is showing the direction of motion. The weight is acting downwards. If the weight is downwards and the ball is moving upwards, force due to air resistance is also downwards. It means the resultant force increases downwards. That means the deceleration or the acceleration is greater, because actually the resultant force is downwards, which means a greater acceleration. But remember, it is moving in the opposite direction, so it is a negative acceleration. And the greater acceleration means the time is going to be smaller. So the average resultant force downwards is greater. So the average acceleration is also greater. So average acceleration is greater. Thus, the time is less. Thus, the time is less. A motor is used to move bricks vertically upwards, as shown here. So bricks must be having a weight which is vertically downwards. So they have a weight which is vertically downwards, but there should be a tension in this material. The bricks start from rest and accelerate for 2 seconds. Time of acceleration is 2 seconds. The bricks then travel at a constant speed of 0.6 for a time of 25 seconds. Finally, the bricks are brought to rest for a further 3.0 seconds. Total mass of the bricks is 25 kilograms. Determine the change in the kinetic energy of the bricks in the first 2 seconds. So change in kinetic energy, because they start from rest. So initial kinetic energy is 0. So I'll just find a half mv squared, which will be a half is 0.5 times the mass, which is 25, times the speed, which is the bricks then travel at a constant speed of 0.64. So that is 0.64, and this is squared. So we check this on our calculator. So this is 0.5 times 25 times 0.64, and this is squared. So that is 5.12. So the change in kinetic energy is 5.12. Then in the next 25 seconds, note that the bricks then travel at a constant speed for the next 25 seconds. They start from rest, they reach to 0.64. So the kinetic energy is the change in kinetic energy is 5.1. In the next 25 seconds, they continue moving with a constant speed. That means the change in kinetic energy is 0, because the velocity is constant. Change in velocity is constant, which means change in kinetic energy is going to be 0, because there is no change in velocity. So this is 0. No change in velocity. Then in the final 3 seconds, They said finally the bricks are brought to rest. That means final velocity is 0 from 25. The velocity is changing from 25, from 0.64 meters per second to 0 in the final 3 seconds. That means, again, we are moving from this kinetic energy of 5.12 back to 0. So the change in kinetic energy is going to be negative. It's going to be negative 5.12. So kinetic energy changes from 5.12 up to 0. So the change is 5.12 joules minus 0, or 0 minus, because the final is 0. Let me start with the 0. So the final is 0 minus, we are already having 5.12 joules. 0 minus 5.1, that gives us negative 5.12 joules. The bricks are in a container. The weight of the container and the bricks is 350 newtons. Calculate for the lifting of the bricks, the container when traveling at constant speed. When traveling at constant speed, the gain in potential energy at a constant speed. So potential energy is equal to mgh. We need to find the gain in height. We have mg is the weight, of course, but what is h? When traveling at a constant speed, then we can find a distance from speed times time, because the speed is constant. So that is very simple. So mg is with the weight, which is 350, times h, which is speed, times time. The constant speed was 0.64 for a time of 25 seconds. So the gain in potential energy will be 350 times 0.64 times 25, which gives us 5,600. So this is 5,600 joules. Then the power required, of course, power is equal to force times velocity. The force is going to, we are doing work against 350 newtons, so the force is going to be 350, and the velocity is 0.64. So the power is going to be 350 times 0.64, which is 224. Also, you would find the power from the gain in potential energy divided by the time taken. Alternatively, I would find power from the gain in potential energy divided by time, which will be 5,600 divided by time, which is 25. 5,600 divided by 25, I think that is 224. Okay, so that is the power. A block is pulled on a horizontal surface by a force P as shown in the diagram here. So we can draw a horizontal line here. So if you are poor at resolving, this angle is 30 degrees. But if you're good at resolving, you don't even need it. You can use the one which is 60. The weight of the block is 180 newtons. The force P is 35 newtons at 60 degrees to the vertical. The block moves a distance 20 meters at a constant velocity. That means the resultant force is 0. The acceleration is 0. Calculate the vertical force that the surface applies to the block. That is the normal reaction. So there is a vertical force which the surface exerts to the block, which is the normal reaction. And if we consider equilibrium in the vertical, it means I have to resolve P in the vertical to point upwards and to be P cos of 60. Resolving P in the vertical to be P cos 60. So it means P cos 60 plus R must be balancing the weight in the vertical. So we shall say P, the normal reaction R plus P cos 60 should be equal to the weight, which is 180. So it means the normal reaction R is going to be 180 minus P is 35 cos of 60. 35 cos of 60. So what is R? 180 minus 35 cos 60. So that is 162.5 or approximately 163 or 160. Then the work done by the force P. Work done is force times distance in the direction of the force. We have distance moved as 20 meters, so we need to find the force in the direction of the distance. So we need to find P in the horizontal, resolving P in the horizontal using 60 degrees to be P sine of 60 or P cos 30. So work done is equal to the force times distance in the direction of the force. And the force is going to be 35 sine of 60 times the distance, which is 20. So just press our calculator. 35 sine of 60 times 20. So that is 606. So I'll write 606. Explain why the block continues to move at a constant velocity although work is done on the block by force P. So if there is work done and it is still moving at a constant velocity, perhaps work done by the force P is equal to the work done against friction. So work done by force P must be equaling to work done against friction. Work done against frictional forces or resistive forces or frictional force. So the work done against frictional force is balancing with the work done by force P. So there is no resultant force in the horizontal. It continues moving with the constant speed. Explain in terms of forces acting why the block remains in equilibrium. So number one, we can begin with the horizontal. In the horizontal, there is a horizontal component of P which is equal and opposite to the frictional force. The horizontal component of P must be equal to the frictional force. That's number one. Number two, the vertical component of P plus the normal reaction must be equal to the weight. So the horizontal component of P is equal and opposite to the frictional force. That's number one. Number two, the vertical component of P plus the normal reaction force is equal and opposite to the weight. That means resultant force is zero. So resultant force is zero. So it is still in equilibrium. Okay, a ball of mass 0.03 kilograms moves along a curved track as shown there. The speed of the ball is 1.3 when it is at A, at a height of 0.31 meters. The ball moves down the track and collides with a vertical wall at point B. The ball rebounds. That is very important. It means it reaches and changes direction. That is very important when dealing with any vector such as momentum. It may be assumed that the frictional forces are negligible. Calculate the change in gravitational potential energy. So that is easy. Change in potential energy is mg times the difference in the height h. So the mass was 0.030 times 9.81 times the change in h. Because it's falling downwards, the change in h is actually negative 0.3. You may put the negative or not. So we check this with our calculator. 0.03 times 9.81 times 0.31. That is 0.091. So I'll just say 0.091 negative. Okay, show that the ball hits the wall at B with a speed of 2.8 meters per second. Note that at A, it had kinetic energy because it was moving. It also had potential energy at A. Then it lost potential energy and gained kinetic energy at B. So we want to find the speed at B. So it means, remember, kinetic energy is equal to a half mv squared. So the kinetic energy at A, I'll call it EK because it had kinetic energy at A, plus the potential energy at A, which I'm going to call EPA. When we combine them, they should give us the kinetic energy at B. When we lose the kinetic energy at A and the potential energy at A, we should be able to get the kinetic energy at B. So at A, kinetic energy is a half times the mass 0.03. The speed at A is 1.3 squared plus the potential energy at A is 0.09, so I will say plus 0.091. This should be equal to the kinetic energy at B by constant if frictional forces are negligible. So at B, kinetic energy will be a half times the mass 0.03 times the velocity at B, which I will call VB squared. So we press our calculator. 0.5, that is a half, times 0.03 times 1.3 squared plus 0.091. Then I multiply this by 2. I divide this by 0.03. Then I find the square root of the answer. That is 2.79. So V is equal to 2.79 or approximately 2.8 meters per second. Okay. The change in momentum of the ball due to collision with the wall is 0.096 kilogram meters per second. The ball is in contact with the wall for a time of 20 milliseconds. Determine for the ball colliding with the wall the speed immediately after the collision. Speed immediately after the collision. So momentum is mass times velocity. And change in momentum is going to be the mass times, let's say, the velocity with which it collides with the wall. I'll call it V1 minus the velocity with which it rebounds. I'll call it V2. Since it rebounds, it will be the velocity with which it rebounds is going to be negative. So the change in momentum is given as 0.096. The mass of the ball was 0.03. V1 is 2.8 minus negative V2, which is plus V2. So we just get V2. So we shall say 0.096 divided by 0.03, then minus 2.8. So I get 0.40. So V is 0.40 when we solve for V2. Then the magnitude of the average force on the ball, the magnitude of the average force on the ball. By definition of force, we know that force is equal to the rate of change of momentum. So the change in momentum was given as 0.096, and the time of contact was 20 milliseconds, so that is 20 times 10 power negative 3. So we have 0.096 divided by 20 exponent negative 3. So that is 4.8 newtons. State and explain whether the collision is elastic or inelastic. So we see that the speed with which it rebounds is 0.40. The speed with which it reached was 2.8. So the relative speed of approach is not the same as the relative speed of separation. Remember, the wall is stationary, so relative speed we subtract. The speed of the wall is 0. So the collision is inelastic. You see that the speed decreases from 2.8 to 0.4, so it means the kinetic energy decreases. So we say kinetic energy of the ball and the wall decreases. So it is inelastic. Alternatively, the relative speed of approach is not equal to relative speed of separation. So you can conclude by saying it is inelastic. It is therefore inelastic. The relative speed of approach is not the same as relative speed of separation. In practice, frictional effects are significant, so that the actual increase in kinetic energy of the ball moving from A to B is 76 millijoules. Actual, if air resistance, if friction effects are significant. Then the length of the track between A and B is 0.60 millijoules. Use your answer in A to determine the average frictional force acting on the ball. So frictional force is going to be the work done against friction divided by distance, because work done is distance, force times distance in the direction of the force. What is the work done against friction? If there was no friction, the gain in kinetic, the increase in kinetic energy would have been 0.091 if there was no kinetic energy. I mean, if there was no resistance or friction. Now that there is friction, it is 76 millijoules, which is 0.076. Then this is going to be divided by the distance, which is 0.60. And this gives us 0.091 minus 0.076 divided by 0.6. So that is 1 over 40, which is 0.025. Define power. I think power is the rate of work done over time taken. That is power, or you can say the rate of doing work. State what is meant by gravitational potential energy. We have already seen that this is the energy of a mass due to its position in a gravitational field. The energy of a mass energy of a mass due to its position in a gravitational field. The energy of a mass due to its position in a gravitational field, that is gravitational potential energy. An aircraft of mass 1,200 kilograms climbs upwards with a constant velocity of 45 meters per second as shown. The aircraft's engine produces a thrust force of 2.0 times 10 power 3 to move the aircraft through the air. The rate of increase in height of the aircraft is 3.3 meters per second. That means the height increases by 3.3 meters every second. That is in the vertical. Calculate the power produced by the thrust. So power is force times velocity. So the force is 2.0 times 10 power 3, then times the velocity, which is 45. So that is easy. 2 exponent 3 times 45. That is 9.0 times 10 power 4, or 90,000. Then determine for the time interval of 3.0 minutes the work done by the thrust force to move the aircraft. Determine for the time interval of 3 minutes the work done by the thrust force to move the aircraft. So work done is force times distance. Is force times distance. But this should be in the direction of the force. So the force is 2.0 times 10 power 3. Then the distance. Remember the height? The speed is 45 meters per second. It is constant. The time is 3 seconds. 3 minutes. So we are going to find the distance from distance is speed times time. The speed is 45. So I'm saying distance. Where should I put this? Distance is speed times time when the speed is constant. The speed is 45. The time is 3 minutes. So 45 times 3. But we change it to seconds, so that is times 60. So this is the distance. So we check this. 2 exponent 3 times 45 times 3 times 60. So that is 1.62 times 10 power 37. So this is 1.62 times 10 power 7. 1.62 times 10 power 7. Alternatively, you can find work done, because work done is energy, which is equal to power times time. You could find the work done from power, which is 9.0 times 10 power 4, then times time, which is 3 times 60. You can also check that. 9 exponent 4 times 3 times 60. It is the same thing. 1.62 times 10 power 7 in joules. Yeah, if power is energy over time or work done over time, then work done can be power times time. Then the increase in gravitational potential energy. So increase in potential energy is equal to mg times increase in the height. So this is going to be m, which is I think 1200. G is 9.81 times height. Remember, in every second, the increase in height was 3.3 meters in every second. In 1 second, the increase in height was 3.3 meters. Now we have 3 times 60 seconds. So it means the height is going to be 3.3 times 3 times 60 seconds. So this is going to be 3.3 times 3 times 60. That is going to be the height. If in 1 second the height increases by 3.3 meters, how about in 3 times 60 seconds? We just multiply. So this is going to give us 1200 times 9.81 times 3.3 times 3 times 60. So that is 6.99 times 10 power 6. 6.99 times 10 power 6, or 7.0 times 10 power 6. Then the work done against air resistance, work done equals to, this is the increase in gravitational potential energy, and this is the work done against the thrust force. Work done by the thrust force to move the aircraft, but this is the increase in gravitational potential energy. So we see that there is a difference. Part of it must be work done against friction or air resistance. So work done against air resistance is going to be 1.62 times 10 power 7 minus 7.0, or 6.99 times 10 power 6. So 1.62 exponent 7 minus 6.99 exponent 6. So that is 9.21 exponent 6. So this is 9.21 times 10 power 6 joules. Use your answer in B part 3 to calculate the force due to air resistance acting on the aircraft. So since we have the work done against air resistance, then the force due to air resistance is going to be equal to the work done against the air resistance over the distance, which is going to be 9.21 times 10 power 6 divided by the distance. Of course, the distance is 45, that is speed times time. 45 times time is 3.0 minutes times 60 to change it to seconds. So this is going to be divided by 45 times 3 times 60. So that is 1.1 times 10 power 3, 1.1 times 10 power 3 in newtons. With reference to the motion of the aircraft, state and explain whether the aircraft is in equilibrium. Of course, the velocity was constant, so it has constant velocity, which means no resultant force. So no resultant force, hence in equilibrium. Hence it is in equilibrium. Okay. State what is meant by kinetic energy. That is energy of a mass due to motion. Energy of a mass due to motion. That is kinetic energy. Energy of a mass due to its speed. That is kinetic energy. A cannon fires a shell vertically upwards. It is vertically upwards, so G is going to be negative if it is required in calculations involving equations of motion. The shell leaves the cannon with a speed 80 meters per second and a kinetic energy of 480. So we can find the mass from that. The shell then rises to a maximum height of 210. The effect of air resistance is significant. show that the mass of the shell is that. So kinetic energy is equal to a half mv squared. Kinetic energy is 480. This is equal to a half times the mass times 80 squared. So I just cross multiply. So 480 times 2 divided by 80 squared. So the mass is 0.15. So m is 0.15 kilograms. For the movement of the shell from the cannon to its maximum height, calculate the gain in potential energy. Gain in potential energy. So potential energy is equal to mgh. It moves, the shell then rises to a maximum height of 210. So this is going to be, the mass is 0.15 times g, which is 9.81 times h, which is 210. So we check 0.15 times 9.81 times 210, which gives us 309 or 310. So this can be 309.0 joules or 310 joules. Then the work done against air resistance. So you see the gain in potential energy is not the same as the change in kinetic energy. So it means there's work done against resistance. Work done against resistance is going to be 480 joules minus 310. And I think this is 170 joules. That's the work done against resistance. So they wanted the work done against resistance, that is 170. Then the average force due to the air resistance acting on the shell as it leaves from the cannon. So since we know that work done is equal to the force, resistive force times distance. So the resistive force, I'll call it FR. Resistive force is going to be work done, which is 170 over the distance, which was 210. So we check this, 170 divided by 210. So that is 0.81, 0.809 or 0.95, which is approximately 0.81 newtons. The shell leaves the cannon at time t equals to 0 and reaches maximum height at time t equals to t. On the figure, sketch the variation with time t of the velocity of the shell from t equals to 0 to t equals to t. Numerical values of v and t are not required. So since it starts with a certain velocity, is projected with a certain velocity, our graph starts from a certain value. At maximum height, v is 0. V at maximum height is 0. So the graph at t, if it reaches maximum height at t, time equals to capital T, so the graph must touch the x-axis. But remember, as it is moving, air resistance was significant, meaning that the resultant force was actually decreasing because of air resistance. Actually, the resultant force was increasing because it was moving upwards, and yet the air resistance would therefore be downwards. So the resultant force downwards was actually increasing. Therefore, the velocity is going to be decreasing. The velocity is going to be decreasing, and the rate at which the acceleration is decreasing also reduces. So the graph is going to be like that. So for you with a pencil, you can draw a smooth curve. Mine may not be very smooth because I'm drawing on a computer. Okay, so the magnitude of the gradient, remember the gradient is the acceleration. So you must show that the acceleration decreases as or the deceleration decreases because air resistance is increasing. So the deceleration decreases because the air resistance is increasing. The force due to the air resistance is a vector quantity. Compare the force due to air resistance acting on the shell as it rises with the force due to air resistance as it falls. Let's check when it is rising. I hope this was when it is rising. Okay. So let's look at initially when it is rising. If it is rising, the weight is downwards, the motion is upwards. This is motion. So the force due to air resistance is going to be downwards. Remember, it is rising. What is happening to the speed? The speed is decreasing. That means the air resistance downwards decreases. So the resultant force downwards decreases. And in the second case, when it is falling, if it is falling downwards, remember the weight is downwards, then we are saying motion is also downwards. The air resistance will be upwards. Force due to air is upwards, which means that now the resultant force here is going to be smaller as it moves downwards. It gains speed downwards, air resistance increases upwards. So it means the resultant force in the second case is going to be smaller because the air resistance increases upwards. So let's look at this scenario. As the shell rises, the force is the air resistance force is downwards. So the force decreases as the speed decreases when the ball is moving upwards. So as the shell rises, the force is downwards. That is the force due to air. The force is downward. The force is downward. So the force decreases. So the force decreases. That is the force due to air. It decreases. So the force decreases as the speed decreases. When the body is going upwards, the speed is decreasing. So the force due to air resistance decreases. So the speed decreases. And as the shell falls, and as the shell falls, we see that as the shell falls, the force is upwards. The force due to air resistance is upwards. That means the force is going to increase because when the object is falling, speed is increasing. When the object is falling, the speed is increasing. And as the shell falls, the force is upwards. That is force due to air resistance. Force is upward. So the force increases since the speed increases. The speed increases as it falls. Okay, the speed increases as it falls. Define work done. So I hope I've made this myself clear. The force I'm talking about here is force due to air resistance. As the shell is rising, the force due to air resistance is downwards. But remember, when it is going upwards, the speed is decreasing. The force due to air resistance only increases when speed increases. So it decreases when the body is going upwards. When the body is falling downwards, motion is downwards, the speed increases downwards. So it means the force due to air resistance is upwards and it increases because the speed is increasing downwards. Define work done. So we have already seen that power is work done divided by time taken. That is power. A car of mass 1,700 kilograms moves in a straight line along a slope that is at an angle of theta to the horizontal as shown here. Okay. The car moves at a constant velocity of 25 for a distance of 25 meters. Air resistance and friction provide total resistance of 440 that opposes the motion. So there is a resistance downwards which is 440 newtons for air resistance from friction. For the movement of the car, state the change in kinetic energy. They said it is constant velocity, so there is no change in velocity, or the change in velocity is zero, so the change in kinetic energy is zero. In other words, the car is moving with a constant kinetic energy. Calculate the work done against the total resistive force. So work done is going to be the resistive force times the distance in the direction of the resistive force, or parallel to the resistive force. The total resistive force was given as 440 and the distance is 25 meters. So 440 times 25, that is 1100 joules. The movement of the car in B from A to B causes its gravitational potential energy to increase by 4.8 times 10 power 4 joules. That is the increase in gravitational potential energy. Calculate the increase in the vertical height h of the car for its movement from A to B. So we know that the change in potential energy is equal to mg times the change in the value of h. So it means our h is going to be the increase in potential energy 4.8 times 10 power 4 divided by m. I think the mass was given as 1700 times g, which is 9.81. So 4.8 exponent 4 divided by 1700 times 9.81. So that is 2.88. 2.88 or approximately 2.9. Then angle theta, since we know the height, so we can find the angle theta. So I have the height is 2.88 and this distance was 25. We want to find that angle theta. So this was A, that was B. So opposite hypotenuse, that is sine. So sine theta is equal to the opposite 2.88 divided by hypotenuse, which is 25. So theta equals to the sine inverse of 2.88 over 25. So shift sine inverse of 2.88 divided by 25. So that is 6.61. 6.61 degrees. Then the engine of the car in B produces an output power of 1.7 to move the car along the slope. That is the output power. Calculate the time taken for the car to move from A to B. So this is the output power. What is the total work done by the car? Because part of it gives it potential energy and part of it is work done against resistance. So total work done by the engine of the car is going to be equal to the one which gives it gravitational potential energy, that is 4.8 times 10 power 4 plus there is this one which is against resistive forces, which is 1.1 times 10 power 4 plus 1.1 times 10 power 4, and I think this gives us 5.9 times 10 power 4. That is total work done by the engine or by the car. So let's find the power. We know power is equal to work done divided by time taken. Let me write work done, because when I write WD, it looks like work times distance. So this is work done divided by the time. Since we have the total work done and they have given us the output power, we can find the time. So the time is going to be the total work done, which is 5.9 times 10 power 4, divided by the output power, which is 1.7 times 10 power 4. 5.9 exponent 4 divided by 1.7 exponent 4. So that is 5.9, which is 3.47 or 3.5. A child moves down a long slide as shown in the figure. The child moves from rest. So that means initial velocity is 0. An average resistive force of 76 newtons opposes the motion of the child. So there is a resistance of 76 newtons. The kinetic energy of the child at y is 300. The decrease in gravitational potential energy of the child as it moves is 3,200. You see that the decrease in gravitational potential energy is not the same as the kinetic energy at y, meaning there is resistive forces. If there was no resistive forces, the potential energy, the decrease in potential energy at y should be equal to the same as the kinetic energy at y. So determine the ratio kinetic energy of the child at y when the resistive force is 76, that is 300, over kinetic energy of the child at y if there was no resistive force. If there was no resistive force, the change or decrease in gravitational potential energy when the child reaches y would be the same as the gain in kinetic energy at point y. So the ratio here is simply going to be 300 divided by 3,200, which is going to be 300 divided by 3,200, which is 0.094. Okay. Use the answer in A to calculate the ratio speed of the child at y when the resistive force is 76 newtons over speed when there is no resistive force. So we know that kinetic energy is a half mv squared. In other words, E is directly proportional to v squared. So we make V the subject. If you're a poor mathematician, you can use this. So this will be twice kinetic energy over mass. So let's look at the ratio. So the ratio will be when the resistive force is 76, when the resistive force is 76, so this will be twice, square root of twice, the kinetic energy is 300 divided by m. Then when there is no resistive force, if there was no resistive force, the kinetic energy would have been 3,200. So this is 2 times 3,200 divided by m. You see that m cancels, 2 has cancelled. So it means the ratio is going to be equal to the square root of 300 over 3,200, which was the square root of 0.094. So root of the answer, that is 0.31. Calculate the length of the slide from x to y. Length of the slide from x to y. So first of all, we have seen if there was no friction, the kinetic energy at y would be 3,200, which is the same as decrease in gravitational potential energy. So we can find the work done against friction. Work done against friction, which is simply 3,200 minus 300. And I think this is 2,900 joules. So the length is going to be, work done is force times distance. So length, which is distance, is going to be equal to the work done against friction over the friction force, over friction force. So the work done is 2,900 over the friction force, which is 76 newtons. So 2,900 divided by 76 newtons. So that gives us 38.1, or approximately 38 meters. At end Y of the slide, a child is brought to rest by a boat. Is brought to rest. That means final velocity there is 0. Sorry. A spring connects the board to a fixed point. The spring obeys Hooke's law. That means F is equal to Kx. That means elastic potential energy will be Kx squared. The child hits the board so that it moves to the right and compresses the spring. The speed of the child becomes 0 when the elastic potential energy of the spring has increased to its maximum value. When the elastic potential energy has increased to its maximum value. So we know that elastic potential energy, what is wrong with this? So elastic potential energy E is going to be equal to a half Kx squared. So the maximum elastic potential energy is 140. This is equal to a half. K was given as 63, then times x squared. So we make x the subject, so I'll say 140 times 2 divided by 63, and I find the root of the answer, which is 2.1. So the maximum compression is 2.1. X is equal to 2.1. Calculate the percentage uncertainty, calculate the percentage efficiency of the transfer of kinetic energy of the child to the elastic potential energy of the spring. So the maximum elastic potential energy is 140, but the kinetic energy was actually 300, because it is the kinetic energy of the child which part of becomes elastic potential energy. So efficiency is equal to the elastic potential energy is 140 divided by the energy input, which is 300 from kinetic, then times 100. 140 divided by 300 is the input, times 100, which is 46.6 recurring, that is 47%. The maximum compression of the spring is x naught. On the figure, sketch a graph to show the variation of the elastic potential energy of the spring with its compression x, from x equals to 0 to x equals to x naught. Of course, when x is equal to 0, the elastic potential energy is 0. But as x increases, the elastic potential energy increases, and it increases rapidly until, of course, there is a limit for x. So the elastic potential energy should be increasing as x increases. So the graph will have an increasing gradient up to x naught. It is not a straight line, it is just a curve. I'll increase the thickness, because elastic potential energy is directly proportional to x squared. So elastic potential energy will increase more rapidly as x increases, like that. So that is increasing gradient. Okay. Next, define power. So this is the rate. of doing work. Avoid starting answering by stating part of the question that power is just a rate of doing work done over time taken. That is power. Use the definition of power to show that the power P transferred by force is given by power equals to FV. So we know that, first of all, power is the rate of doing work, and work done is equal to force times the distance in the direction of the force. So it means the work is equal to force F times the distance, which I'm going to call the displacement X. Let me change this to displacement instead of distance. So it is force times displacement. So that is F times X. So that means now power is equal to the work done over time taken, which is going to be force times displacement over time. And force times displacement over time, that is force times velocity as required. A block is pulled up a slope by a wire attached to a motor as shown here. So we can try to first find its masses because its weight acts vertically downwards, which is m times g. If we resolve this perpendicular to the plane, it will be mg cos of 11 degrees. Down the plane, it will be mg sine of 11 degrees. So there is tension there in the wire. The useful output power is 56. The block has a weight of 430, that is mg is 430. It travels with a constant speed along the slope at an angle of 11 degrees. Assuming that there is no resistive force opposing the motion of the block, calculate the tension T. Since it moves with a constant speed, the resultant force along the plane is 0. That means the tension in the wire upwards is equal to the force downwards, which is mg sine theta or sine 11. So that means T is going to be equal to mg, which mg is 430. Mg is 430 sine of 11 degrees. So 430 sine 11, that is 82. So the tension is 82 newtons. Then calculate the speed of the block. Calculate the speed of the block. So since we already know that power is equal to force times the velocity or speed, so it means the speed is going to be the power. I think they gave us the power as 56. The power output was 56 divided by the force, which is 82 newtons. So this means the speed is going to be 56 divided by 82, and that is 0.68 meters per second. The rate of increase of gravitational potential energy of the block is equal to the useful output power of the motor. One of the reasons for this is that there is no work done against resistive forces. By considering the motion of the block, state another reason for this. Yes, there is no work done against resistive forces, but the block was moving at a constant speed. That means there is no change in kinetic energy. So that means the rate of increase of gravitational potential energy is still equal to the useful power output of the motor. So we simply say at constant speed, at a constant velocity, there is no change in kinetic energy. There's no change in kinetic energy. At constant velocity, there is no change in kinetic energy. So since there is no work done against resistive forces, there is also no change in kinetic energy. Then it means the increase in gravitational potential energy, or the rate of increase in gravitational potential energy, is the useful power output of the motor. The motor has efficiency of 80%. Calculate the time taken for an input of 1.2 kilojoules to be supplied to the motor. So efficiency is equal to power output divided by power input, of course, times 100. So 80% is 0.8, or 8 over 100. So 8 over 100 will be, the power output was 56. The power output was 56. Let's first find the power input. So the power input is 56 divided by 0.8. 56 divided by 0.8. So that is going to be 70 watts. Power input is 70 watts. But we want the time taken for the input energy to be 1.2 kilojoules. So we know the input power, and time taken is going to be, we know that power is energy over time anyway. So it means our time is equal to energy over power. Power is equal to energy over time. So it means the time is going to be the input energy divided by the power. So the input energy is 1.2 times 10 power 3 divided by the input power, which is 70 watts. So 1.2 exponent 3 divided by the answer. So that is 17 seconds. Okay, we move to the last question in work, energy, and power. An archer releases an arrow towards a target at a velocity of 65 meters per second at an angle of 4.3 degrees above the horizontal, as shown here. Okay. When released, the tip of the arrow is a horizontal distance 70 meters from the target and 1.66 meters above the horizontal ground. The arrow hits the center of the target. In other words, it is moving through a projectile. So it is going to move in a projectile because it hits the center of the target. Assume that air resistance is negligible and that all the mass of the arrow is at its tip. Show that the time taken for the arrow to reach the target is 1.0 seconds. So time is equal to the displacement over velocity. Displacement divided by the velocity. Or I can consider horizontal motion. Consider horizontal motion. Consider horizontal motion and use S equals to UT. Because air resistance is negligible, acceleration is going to be constant, UT plus a half AT squared. Remember, in the horizontal, acceleration is 0, so this part is 0. Acceleration in the X is 0. So S is 70 in the horizontal. Initial velocity in the horizontal, we resolve the velocity to the horizontal, which will be 65 cos 4.3. So this is going to be 65 cos 4.3. So this is equal to, what is this? So 70 equals to 65.0 cos of 4.3 degrees, then times t. So when you make T the subject, T is equal to 70 divided by 65 cos of 4.3. So 70 divided by 65 cos 4.3. So that is 1.07996, which is approximately 1.08 seconds. Calculate the height of the center of the target above the ground. The height of the center of the target above the ground. We want height, that is distance, of the center of the target above the ground. So let's first find its displacement by the time it hits the target. So displacement, that is now vertical motion. I'm considering vertical motion because the height is in the vertical. I'm going to consider vertical motion. So displacement S is equal to UT plus a half AT squared. In the vertical, we are finding the displacement. Initial velocity in the vertical, we resolve 65 in the vertical, it will be 65 sine of 4.3 in the vertical. Then times the time is the same, which is 1.08. Because it moves vertically upwards, it will be minus, acceleration will be negative, so minus a half times 9.81, then again times t, which is 1.08, but this is squared. So we press our calculator, 65 sine 4.3 times the time, which is 1.08, minus, open brackets, 0.5, that is a half, 9.81 times 1.08, and that is squared. So we are seeing that the vertical displacement is even negative, meaning it has gone below the point of projection. So S is equal to negative 0.46 meters. Yes, negative 0.46 meters, meaning it falls 0.46 meters below the point of projection. It falls 0.46 meters below the point of projection. But from the diagram, you see that the point of projection is 1.6 meters above the ground. The point of projection is 1.66 meters above the ground, but this one falls. It falls 0.46 meters below the point of projection. That means now, since we want its height, we want the height above the ground, we just subtract. So height above the ground is equal to 1.66 minus 0.46, which is, I think that is 1.2. So that is 1.2 meters. Last but not least, by considering energy changes, state and explain how the final kinetic energy of the arrow as it hits the target compares with its initial kinetic energy immediately after release. Final kinetic energy as it hits the target compares with its initial kinetic energy immediately after release. A numerical calculation is not required. So we noticed that actually the gravitational potential energy has decreased, but since our total energy is conserved, it means the kinetic energy has increased. It has fallen below the point of projection. So it means the gravitational potential energy has decreased because it fell below the point of projection. So I'm saying gravitational potential energy decreased. It fell below the point of projection, meaning if this was the level of projection, it fell slightly below the level of projection, which means that the gravitational potential energy here is not the same as the gravitational potential energy here. So the gravitational potential energy has decreased or decreased, but since total energy is conserved, since total energy is conserved, the decrease in gravitational potential energy must be equal to an increase in kinetic energy. So it means kinetic energy has increased. Kinetic energy has increased. Of course, if it falls below the point of projection, it even lands with a speed higher than the one with which it was projected. So it means the kinetic energy increases further. Okay, so that is the end of work, energy, and power, and I would like to wish you all the best. See you in force, density, and pressure. Bye bye. Stay blessed.